Causality, omitted variables, and sample selection. Common problems with regression 2. Regression results in causality. So the regression coefficient on x1 tells us how x1 and y are related. But it doesn't tell us that x1 causes y. So regression does not establish causality. It establishes association. How can we really tell if x1 is causing y? We really can't know for sure. But just thinking it through can help a lot. So one of the ways to think it through is to give it a sniff test. Is it plausible that x1 causes y? You know it is. You know that for your model, you had to justify it based on the literature. So all of your projects passed the sniff test. Plus we were sniffing too, Mohammed and I. Is it possible that the causality also runs the other way? For example, income contributes to health, right? We said that health is a function of income, but might health also contribute to income? In other words, might income be a function of health? It might, right? Because if you're healthier, you can work harder, you'll be more productive. So that's the problem of reverse causality. Another example is that more education increases income. So your model might be income is a function of education, but it's also true that education is a function of income, because if you're richer, you can buy more. One way to get around potential reverse causality problems is to take advantage of timing. For the education and income example, you could see whether education in the past affects later income. So let's say your project now is looking at the effect of education on income in 2010. Well, one thing that you could do is look at education 10 years ago and see if it affects the income of countries today. An even stronger test of the proposition that education causes income is to see whether education in the past affects future changes in income. And that way you're not confounding the fact that income is correlated over time. So you're really trying to separate out the education, what effect the education is having. You can address the health question in the same way, using income in the past to predict later health or changes in health. The basic idea is to use different times so that the two variables can no longer cause each other. Omitted variables. Did your model leave something out? You included only one control variable, the x2, and that was right. You were supposed to do that. I only let you include one control variable. But is there something else that is predictive of y that makes sense to control? Why it's important to include more controls. If you leave out something important in predicting y, the other x's might be standing in for that omitted variable. That's why in the example provided in the regression lectures from last week, income had a smaller effect on life expectancy once spending as a percent of GDP was included. Income was standing in for percent of GDP dedicated to spending because the two measures are correlated, but they're not perfectly correlated. So including the both variables allows you to separate out the independent effects of both. It allows us to measure the effect of income holding other relevant variables constant. Okay, so let's say we didn't control for x2. We're going to get the wrong idea about how important income is. Because when we include x2, which is how much we're spending on health as a percent of our income, we learned that its income is important, but it's also important how you spend that income. And that makes perfect sense. You get a better measure of the effect of income itself when you're controlling for the other things that affect your y variable. So here's the recap. If you leave something out of the model that belongs, your estimates of the effects of the variables you include might be wrong. You get a better measure of the true effect of x1 when you include other variables that also cause y. Sample selection. Sometimes the people or countries that provide data are not representative of all people or all countries. If that's the case, your estimates might only be true for some groups of people or countries. So here's a really good example. You may have heard of Alfred Kinsey. Kinsey wrote about sexuality in the United States in the late 1940s and 1950s. He found that people were super racy in the United States. But his subjects were not representative of the U.S. population. They were mostly college students, prisoners, and prostitutes. What do those three groups have in common? Well, they have more sex than the general population. And even in these groups, he was talking to the people who were willing and wanted to talk about sex. So they're likely to be more sexually active. Because of the sample selection, Kinsey's results overestimated how much sex was happening in 1950. And his results really gave no information about sex for the population as a whole. So that's a really good example of sample selection. When you have sample selection, it makes it really hard to say anything. So which countries were excluded from your study? How many were excluded? Were they poorer, smaller, maybe concentrated in one region? If so, well, actually, if it's the other way, if the countries excluded are just like the countries that were included, you don't have to worry so much. If you have a random sample from a population, you're good. You're getting everyone. It's representative. Even you don't need to survey everyone to know what's going on in the population. But if your countries were poorer, smaller, and concentrated in one region, then you may have a problem. And I want you to think about how might sample selection change how you interpret your results. Can you say for sure that your results apply to countries that were excluded? And again, if you had a random sample, it wouldn't be a problem. But if it's non-random, if the countries that report data are richer and sort of more together than the other countries, then you'll have a problem. Okay, up next, we're going to go over the last 4 common problems with regression results.